So now we're going to get into logic gates. They're the most basic part of a computer, and they've been around since the earliest computers, where they had different gears acting as logic gates, and eventually that turned into your relay switches and vacuum tubes all the way up to your transistors. Now we have billions of logic gates on a single processor, and those logic gates are responsible for adding, subtracting, multiplying, dividing, all sets of data that you have on your microprocessors. There are 6 main types of logic gates, 6 different logic gates elements. First one you'll see usually is the NOT, and it's just a triangle with a circle at the end of it with a single line running through it. So that's the NOT gate. And what the NOT gate does is it negates every value that goes through it. So if you have a 1 going through it, going into a NOT gate, it'll turn it into a 0, and a 0 will become a 1. All logic gates work in binary, so 1 represents true, 0 represents false, and NOT will turn a true to a false to a true. The second type of gate is going to be our AND gate, and it looks like a D with 2 lines going into it and 1 line coming out. You need to make sure that this back line is flat, because if you accidentally curve it, it will look like a OR logic gate. So this is our AND. And our AND logic gate gives out a 1 only if both the inputs are 1. And by 1, I mean if you turn on both of these wires, the AND gate will also give out a ON signal or a ON wire. Okay? Otherwise, if you only have 1 input lit up and 1 input not lit up, you'll get no output on the AND gate. And then our next logic gate is going to be our OR gate, our XOR gate actually, because our XOR gate is processed next in our order of operations. So this is XOR. Most people will call it exclusive OR or the XOR gate. I just call it XOR gate because that's what I first heard. So the XOR gates will take 1 input or the other and not both. The difference between the XOR and the OR gate is that the OR gate will take both inputs, the XOR gate will only take 1 input. So if you have both inputs on, the XOR gate will turn a 0, and if you have one on or the other one on, it'll return you a 1. And our OR gate looks pretty much like the XOR gate, but it does not have that extra line there. Okay? And that's our OR gate. I'm going to add that R there. And then after that, we have our 2 other negations. And negation means opposite, or changing one value to its opposite value. So our other 2 negations are our AND gate, and it's the D with a circle at the end, and it does pretty much the opposite of what the other AND gate does. So this is our NAND gate, negate, and this gate will return a 1 if both inputs are off. Fairly simple enough. And then our OR gate is just like our other OR gate, our NOR gate, N-O-R, negate for OR. Our NOR gate will have a circle at the end, like that. So this is how you represent the logic gates pictorially in pictures. There's 2 other ways to represent our logic gates in computer science, or you can also represent them in Boolean algebra, but we won't get into that. So the other 2 ways is our, we'll call it arithmetic or math way. I'm just going to label it as math. And if you want to represent the logic gates, math will make sense on paper. Okay? So for math, our NOT gate is just a line above any variable. In this case, our variable will just be a, and that's not. Line, it turns a 0 to a 1 and 1 to a 0. Our AND gate will look like a asterisk. An asterisk is basically a multiplication symbol in math, and it works the same way. If you multiply a 1 by a 1, it's going to be a 1, and if you multiply a 1 by a 0, it's going to be a 0. So both of them have to be 1 for you getting a 1. Our XOR gate in math is a plus with a circle around it, and our OR gate is a plus. Now, if you do 1 plus 1, you get 2, which is pretty much the same in a binary. It'll just have a carry bit. But 1 plus 0 and 0 plus 1 equal 1. Now, with the plus sign with a circle around it, that means that you can't have your 1 plus 1. You can only do 1 plus 0 or 0 plus 1. Okay? And your NAND and your NOR gate is a combination of these 4 gates up here. So a NAND gate would look like you'd have your asterisk for your AND gate. You'd have 2 variables. We'll just call them A and B. And then you draw a line above it. That's your NAND gate. And your NOR gate would be the same thing, but instead you have a plus sign. You have your line above it. Okay, so in Java, we represent these logic gates with separate symbols than we do in math. In Java, there are 2 symbols for the NOT. You'll have a exclamation point, or you will have like the squiggly line above the N in Spanish. On their keyboards, it's called the grav key. And then for AND, we will be using the ampersand. Ampersand kind of sounds like AND. Now, for Java, you'll have a single ampersand and then a double ampersand. The single ampersand will operate on a binary level, so don't worry about that right now. The double ampersand is the AND gate that we normally know. For the XOR gates, we have a caret, or a upwards arrow looking thing. On our calculators, we call them carets, and they're usually used for exponential functions, but it's our XOR gate. And our OR gate is a single line or a double line. The double line is going to be the one that we use right now. Okay, so this is going to be our programming. /Java symbols. So, after we know all of our types of logic gates, we're going to have to look at a order of operations for them. Most people just remember the acronym NACSO. Okay, in Java, this is the way that these operators are looked at left to right, kind of like in math. We'll have multiplication and addition. Well, if you remember that multiplication comes before addition, you'll see it over here. Multiplication is AND, addition is O, and it comes after each other. And the N would be like putting something in parentheses and negating it. So this is N for NOT, A for AND, X for XOR, and O for OR. And you'll read them left to right and do them in that order.